Hello everyone and welcome. Today we're diving into the fascinating world of Wi-Fi technology. We'll cover its history, how it works, key features, security protocols, and what the future holds with Wi-Fi 6 and Wi-Fi 7. Let's take a quick trip through the evolution of Wi-Fi. It all started back in 1997 with Wi-Fi 0, also known as IEEE 802.11, offering just 2 megabits per second, but it laid the foundation for wireless networking. Then in 1999, we got both Wi-Fi 1, 802.11b, and Wi-Fi 2, 802.11a. Wi-Fi 1 prioritized compatibility and range, while Wi-Fi 2 brought higher speeds, but at the cost of coverage. Wi-Fi 3 arrived in 2003 with the 802.11g standard. Combining the benefits of both earlier versions, it quickly became the home Wi-Fi standard. Wi-Fi 4, or 802.11n, launched in 2009 and introduced MIMO technology, significantly boosting speed and reliability, especially in crowded networks. In 2013, Wi-Fi 5, 802.11ac, pushed things further with gigabit speeds and the use of the 5 GHz band, perfect for HD streaming and gaming. Then came Wi-Fi 6, 802.11ax, in 2020, focusing not just on speed, but also on handling more devices efficiently, improving battery life, and performing better in busy environments. And in 2021 we got Wi-Fi 6E, expanding into the 6 GHz band. This means less congestion, lower latency, and more bandwidth. Ideal for future tech like AR and VR. From the humble beginnings of Wi-Fi 0 to the advanced capabilities of Wi-Fi 6E, the journey of wireless internet has been nothing short of incredible. And with Wi-Fi 7 just around the corner, the future is looking faster than ever. Let's start with the physical layer functions. Wi-Fi 4 introduced MIMO, or multiple input multiple output, which allows multiple antennas to transmit and receive data. However, only one device could communicate with the router at a time. This was fine for basic tasks like web browsing, but streaming video could slow down. Now multiple user multiple input multiple output was introduced with the Wave 2 of Wi-Fi 5. It allows multiple users to communicate with the router at the same time. They don't want to wait their turn. It breaks up the bandwidth and pushes to the devices. So internet speed is very high and increase the performance. Wi-Fi 6 has a lot of features. BSS coloring, basic service set coloring. TWA, target wake-up time. Basic service set coloring marks shared frequencies to allow Wi-Fi 6 access points to determine whether simultaneous use of spectrum is permissible. This technology reduces interference due to congestion and ensures consistent service to multiple connected devices in high-density environments. Target wake-up time allows the Wi-Fi radio and battery-powered devices to enter a sleep mode when they are not exchanging data. Multiple user multiple input multiple output also use advantages of beamforming. Beamforming is a technique that sends transmission in a specific direction. Without beamforming, the transmission is sent in every direction, which can weaken the signal. With this technique, the signal is directed to the devices that are connected to that. Next, let's talk about multiplexing. Spread spectrum combines signals from several sources to fit into a larger bandwidth. It's specially defined for wireless networks. Older generations, Wi-Fi 1, 2, 3, 5 were based on OFDMA, orthogonal frequency division multiplexing. It is a frequency division multiplexing mechanism, which works by dividing a single wideband signal into a large set of narrowband subcarriers in such a way that all of the subcarriers are evenly spaced and orthogonal to each other. It increases in channel bandwidth, providing more bandwidth, but each channel was fully reserved to a single user for each transmission. It divides the available spectrum into frequency channels, allowing each user to use two channels simultaneously for communication. One for transmitting information to the network and the other for receiving information from the network, referred to as uplinks and downlinks. One of the most important new features of Wi-Fi 6 is OFDMA, orthogonal frequency division multiple access, which allows one transmission to deliver data to multiple devices at once. This technology enables a router and its connected devices to utilize bandwidth more efficiently by reducing the time between data transmissions. This results in more bandwidth available for other devices. Now move on to frequency bands. For many years, 2.4 GHz was a popular choice for Wi-Fi users. It is the standard band, but that is used in a lot of other devices such as microwave ovens, Bluetooth, cordless phones, and wireless cameras. Because of that, the signal became overcrowded and was causing a lot of interference with Wi-Fi signals. Then it slows down the Wi-Fi network speed and loses connection. To solve this issue, dual-band routers were created. These routers contain two types of wireless radios that could simultaneously support connections on both 2.4 GHz and 5 GHz links. By default, devices in the range of a dual-band router would automatically connect to the faster, more efficient 5 GHz frequency. However, if a device was further away or behind walls, the 2.4 GHz could be used as a backup. Because higher frequencies have a harder time penetrating solid objects, 2.4 GHz has a longer range than 5 GHz, but the data transmitting rate is slow. The 6 GHz band, introduced with the new Wi-Fi 6E standard, provides the least coverage but transmits data at the fastest speeds of the three frequencies. Wi-Fi 5 had a maximum speed of 6.9 gigabits per second, but with Wi-Fi 6 and 6E has 9.6 gigabits per second. Wi-Fi 6E provides 2.3 gigabits per second per device. When it comes to the channel frequency spectrum, the 2.4 GHz band is divided into 14 channels spaced 5 MHz apart. It operates between 2.402 and 2.483 GHz. It has a total of 14 channels with 3 non-overlapping channels. Because of overlapping, they aren't all usable at the same time. Channels bonding. Channel bonding can combine multiple channels to transfer a message and achieve high speed. Channel bonding reduces the number of channels, increase bandwidth, and improve the network access rate. Larger bandwidth means that more devices are supported with better overall performance. For example, 20 MHz channel can be bonded into a 40 MHz channel. Then two bonded 20 MHz channels do not interference with bonded into a 40 MHz channels. 5 GHz has more channels with 25 non-overlapping channels in 20 MHz bandwidth. If double the channel to 40 MHz, then it has 12 channels only. When it comes to 80 MHz, it has 6 channels with large bandwidth, and when 160 MHz, it has 2 channels. Modulation. Modulation and its types prevent the interference of the message signal from other signals. 802.11 Wi-Fi can use different digital modulation schemes for data transmission. BPSK, binary phase shift keying, is used for lower bit rates with Wi-Fi 3. BPSK technique is the simplest among all the PSK, phase shift keying techniques. In this, each signaling element is represented by a single data bit. Here the carrier undergoes two phase reversals, such as 0 degrees and 180 degrees. In phase shift keying, the digital bit sequence is first converted to a non-return to zero bipolar signal, which directly modulates the carrier wave. The bit sequence gets changed either from 1 to 0 or from 0 to 1. When the bit sequence changes from 0 to 1, then we notice a positive phase change, whereas when the bit sequence changes from 1 to 0, then a negative change of phase is noticed. QPSK, quadrature phase shift keying. QPSK modem implementation in conformance to 802.11b Wi-Fi. QPSK is a modulation scheme that allows one symbol to transfer 2 bits of data. There are 4 possible 2-bit numbers and consequently we need 4 phase offsets. Again, we want maximum separation between the phase options, which in this case is 90 degrees. The implementation of the modem functions includes sampling, non-return to zero encoding, QPSK modulation, data packet formation using payload and packet header, receiver matched filtering, QPSK demodulation, and a decision device. QPSK implementation can greatly improve the performance efficiency with less development time and costs for high data rate wireless local area network applications. QAM, Quadrature Amplitude Modulation. QAM is a combination of amplitude and phase modulation. It is necessary to only operate the higher-order modulation formats when the link quality is good, signal strength levels are high and noise levels are low. It is for this reason that dynamic link adaptation is required in wireless communication systems using high-order QAM modulation formats. Wi-Fi 6 uses quadrature amplitude modulation. Higher modulation can increase the data rate. When it comes to data rates, guard interval and spatial stream are very important. Guard intervals. Guard intervals are used to ensure that different transmissions do not interfere with each other, and that transmissions do not overlap in any other way. The standard symbol guard interval used in 802.11 OFDMA is 0.8 microseconds. To increase the data rate, Wi-Fi 4 used a 0.4 microseconds guard interval. To increase coverage area, Wi-Fi 6 used 0.8 microseconds, 1.6 microseconds, and 3.2 microseconds guard intervals. Spatial stream. In the MIMO environment, wireless signals are being transmitted simultaneously from both receiving and transmitting antennas. To avoid collisions, each signal is transmitted via a spatial stream within the given spectral channel. Multiple user MIMO routers come in different variations, such as 2x2, 4x4, and 8x8 likewise. These variations refer to the number of streams that are created. 2x2 means they have 2 antennas for 2 streams. It doesn't mean they can only connect with 2 devices. Streams can be divided and shared with other devices. Wi-Fi 5 only affects the download link. Wi-Fi 6 supports 12 streams with 4 streams on a 2.4 GHz band and 8 streams on the 5 GHz band. It affects both download and upload links. Now let's move on to data link layer functions. Wi-Fi uses CSMA/CA, or carrier sense multiple access with collision avoidance, to prevent data collisions. CSMA/CA is the medium access control method for IEEE 802.11 wireless LAN. The idea here is to avoid a collision rather than allowing it to occur. This is done using our TS and CTS signaling mechanism and NAV. NAV is used for virtual carrier sensing. Here the format of the 802.11 frame. It includes frame control, control information of the frame, duration, time period this frame occupies a channel during one hop, address 1 destination, address 2, transmitter address, which is used to send acknowledgements, address 3, used for filtering by access points and the distribution system, address 4, optional, sequence control, frame number, frame body, data of message, FCS, frame check sequence for error detection. Cyclic redundancy check. The CRC is used to detect transmission errors, while the sequence number is used to avoid frame duplication. When a device receives a correct frame, it returns a special acknowledgement frame to the sender. A cyclic redundancy check is an error-detecting code commonly used in digital communication and storage devices to detect accidental changes to raw data. The most often used method for error detection is to add parity bits to existing data bits before transmitting. Every error detection method uses a certain algorithm to generate parity bits based on existing data bits, and CRC is one of them. Stop and wait ARQ. Error control in the data link layer means two things: error detection and error correction. Sometimes data is lost or damaged during transmission. Error control will inform the sender, specify the frames, and ask for retransmission. This process is called automatic repeat request. In reality, the acknowledgement sent back to the sender also could be lost or damaged. Stop and wait ARQ is a method in telecommunications to send information between two connected devices. It ensures that information is not lost due to dropped packets, and that packets are received in the correct order. It is the simplest automatic repeat request mechanism. The stop and wait ARQ solves the three main problems, but may cause big performance issues as the sender always waits for acknowledgement, even if it has the next packet ready to send. So, stop and wait ARQ may work fine where the propagation delay is very less, for example, LAN connections. Wi-Fi security. Wi-Fi security protocols use encryption technology to secure networks and protect the data of their clients. Wireless networks are often less secure than wired ones, so wireless security protocols are crucial for maintaining online safety. The most common Wi-Fi security protocols today are WEP, WPA, WPA2, WPA3, WPS. WEP, Wired Equivalent Privacy, was developed in 1999. It used a 40-bit encryption key. It was vulnerable and not secure. It was easily hackable, so a better security protocol was needed. WPA, Wi-Fi Protected Access, is another wireless security protocol. WPA is better than WP. It uses a stronger encryption method called Temporal Key Integrity Protocol, and Temporal Key Integrity Protocol dynamically changes its key. But Temporal Key Integrity Protocol did have some vulnerabilities. WPA2 was developed to provide even stronger security than WPA. WPA2 uses the Advanced Encryption Standard. The Advanced Encryption Standard uses a symmetric encryption algorithm. The next generation of wireless security protocol is WPA3. It provides cutting-edge security protocol. It increases protection from password guessing attempts. There is another wireless security method that doesn't require typing in a password. This method is called WPS. There are two methods to access Wi-Fi. Most common method is the push-button method. Another method is entering WPS PIN number. WPS is the easiest way to join a wireless network. Beacon. Beacon frames are used to communicate throughout the service area for the characteristics of the connection offered to cell members. This information is used by clients trying to connect to the networks, as well as clients already associated with the BSS. Future development. The Wi-Fi 7 specification, also known as 802.11b extremely high throughput, isn't even close to being completed. The IEEE's current paper on the current status of 802.11b calls for the standard's ratification sometime in 2024. Wi-Fi 7 will be faster, in part because of wider channel widths. But the key improvement Wi-Fi 7 makes is how it smartly uses what earlier Wi-Fi versions have already provided it. Wi-Fi 7 will significantly increase Wi-Fi bandwidth. According to the IEEE, the maximum nominal throughput of Wi-Fi 7 is 46 gigabits per second, 4.8 times faster than Wi-Fi 6. The average latency will be less than 2 milliseconds, or 60% faster than the previous generation. Wi-Fi 7's most significant improvement is that it transforms the router into a multi-link device. Several physical radios can communicate on separate frequencies. Wi-Fi 7 widens the maximum available channel width from 160 MHz to 320 MHz. Wi-Fi 7 can combine two 160 MHz channels in the high bands to create an effective 320 MHz data channel. Wi-Fi 7 also incorporates preamble puncturing, which is a more aggressive way of handling interference. How Wi-Fi 7 improves the overall experience, however, is both cooler as well as a bit more complicated. Conclusion: Wi-Fi wireless technology was invented in 1977 based on the 802.11i EEE standard. It has been developing since then, and by now we have the main version of Wi-Fi 6. This report includes history, physical layer functions, data link layer functions, and future developments. Thank you for watching. Don't forget to like, comment, and subscribe for more tech tutorials.